So now we'll go over question 3 on CS 186 Spring 2021 final. Um, so this question is about matrix, vector, and matrix multiplication. I believe it looks more daunting than it actually is. So hopefully going over the solutions will help clear things up. Okay, so we are given matrices and we're given some properties of matrices. If you've taken a class like E16A or Math 54, you should hopefully know what multiplying two matrices together or multiplying what a matrix and vector together would mean. If not, there's some definitions here to catch you up. Okay, so the first question is saying, select the sum of A dot val from A where A dot col is equal to A dot row. Essentially, when the column is equal to the row, that means that we are essentially selecting things along the diagonal, which is equivalent to a trace. So the equivalent linear algebra operation is the trace of A here. Okay, then there's this next thing. We're selecting A dot row, A dot col, and then A dot val plus the sum of B dot val and C dot val from A, B, and C, where A dot row is equal to B dot row, B dot col is equal to C dot row, C dot col is equal to A dot col, and then we're doing some group bys. So what this immediately tells me is that we have this A dot val and we're summing B dot val and C dot val. What this immediately tells me is that there is some sort of BC in our output. Potentially, it could still be none of the above, but we can almost immediately eliminate this first option, and we can also almost immediately eliminate this third option. We do have a couple extra columns. I think we can ignore them for the sake of this question. Okay, so let's keep going. So we have this B dot col and C dot row that we're doing an equality of. What this is doing is it's essentially saying in this matrix vector multiplication, the B's rows, each of those column values, and the C's, for C's columns, each of those row values need to be matched together. So that's essentially what a matrix vector multiplication is doing. When we're grouping by A dot row and A dot column and A dot val, so we're grouping at all of these together, the sum of B dot val and C dot val, we're summing everything that multiplies in that row and that column. And we're doing that for every A's row and A's column. Question 3 is basically a subset of question 2 in some ways. So in question 3, we are doing a sum of A dot val and X dot val, where X is a vector, where A dot column is X dot row. So very similar to before, what's going on is everything from this, every column that you're doing is getting multiplied by a particular row. And since we're grouping by A dot row, for every row we're doing this. So for every row, we're multiplying one row by one column, which is why we get AX here. Okay, then this next question. So what we're doing here is we have from A and then X as X1 and X as X2. So now we have two X's, two vectors. And we're saying where X1 dot row is equal to A dot col and A dot row is equal to X2 dot row. So we can see here that we're doing something very similar to a matrix vector multiplication, except now there's a row and a col here, and there's a row and a row here. So what that tells me is that there is some sort of transpose going on with the X. Okay, so what are we selecting? We're selecting the sum of A dot val, X1 dot val, and X2 dot val. So that is A dot val, X1 dot val, and X2 dot val here, where we know that X1's row is A's column and A's row is X2's row. So this is the only option that fits that. Okay, moving on. This part is a little bit less linear algebra heavy. So here's the matrix relation schema again. Um, and so this question's asking us what's the minimum number of pages it takes to store a 100 by 100 matrix. And so what fields we're considering is this relation M. So it has 3 integers. And so what that means is each integer takes 4 bytes. So we have a total of 12 bytes per record. We're given that each page is 1024 bytes. So we want to figure out how many pages, how many records we can fit on a particular page first. And so recall that for fitting records on a page, you don't just need to fit these 12 bytes onto the page. You also need to reserve 1 bit for your bitmap. And so if you do that, one way of doing it is, I believe the solutions did a guess and check approach, but one way of doing it is you could convert everything to bits. So you could convert your 12 to bits and you could add 1 to that for your bitmap, and then convert your 1024 to bits, and then divide that by the result that you get. So divide 1024 times 8 divided by 12 times 8 plus 1. And you'll get that you can fit 84 records onto a particular page. How many records do we have in total? So we have 100 by 100 times 100 matrix. So we have 10,000 records in total. So the number of pages it takes to store the entire matrix is 10,000 divided by 84, which is 120 pages. The next question is also in a similar vein. So it's asking us, now suppose the table for the schema is byte row, byte column, and int val. Where the byte integer is exactly 1 byte. What are the minimum number of pages for a 100 by 100 matrix? So now how long is each record? So each record is 1 byte plus 1 byte plus 4 bytes, because an integer is 4 bytes. So each record is a length of 6 bytes. We still need to maintain 1 bit for our in our header page, or in our header, for indicating whether a record is present or not. So we can fit, much like the calculations that we did previously, we can fit 167 records on a particular page. Again, there are 2 ways of doing this. The solutions did a guess and check approach, but another thing that you could do is convert everything to bits. So convert your 6 bytes to bits, add 1 to that, and then you have 1024 pages on, or 1024 bytes on a page. Convert that to bits, and then take the division of those 2. So if you can fit 167 records, then it will take 10,000, so 100 times 100, divided by 167, will take 60 pages to store the entire matrix.